Adding an SD card to your Arduino instantly gives you access to mass storage. Team this with an LCD screen and you can now display saved images using only your microcontroller. But how do we translate bitmap image files to pixels on the screen? Let me show you how. Hi and welcome to Bytes and Bits. I've done a few videos now working with this LCD touchscreen with the built-in SD card, and I saw in the previous video that we can very easily use some library software to read bitmap images from our SD card and then display them on the screen itself. Now, using libraries is a very quick and easy way of adding functionality into your Arduino sketches, but sometimes it's a bit of a double-edged sword where the libraries that you load can sometimes contain a lot of extra software that you don't actually need, and of course that uses up valuable programming space on your Arduino. So there is another way of doing it where we can have a go at writing our own library software. Now obviously this is a bit more involved and a bit harder, but it's actually a hell of a lot more fun, where we can actually get right down into the nitty-gritty of how these things work. So in this video I'm going to show you how we can look at how a bitmap file is organized and stored on our SD card, and then using the very low-level reading and writing capabilities of our SD card library in the Arduino, we can really read that information in and translate it ourselves. And of course this then means we open up this sort of idea where we can really look at any file type stored on our SD card, and if we've got enough knowledge and skill, we can obviously then program our own libraries to read those files in, or create those files so that we can then transfer them off to other PCs and so on. So let's make a start and have a look at how we can then write our own bitmap file library on our Arduino. To get started, we need to connect up all the hardware. I've covered this in detail in a couple of previous videos, so I'll put links to those up in the top right corner and also down in the description. And I'll also put a link off to the project page on my main website for this, where you can get all of the circuit diagrams and of course download all of the code. Now that we've got our hardware sorted out, we need to have a look at the actual bitmap file format. So any file is really just a series of data bytes stored in a stream as these things called files on a hard drive or SD card. So really, if we read those bytes of information in, obviously they're stored in a certain format and certain bits of them mean certain things. And that's really what we have to have a look at and understand. So if we go to Wikipedia's entry for the BMP file format, this gives us a very detailed explanation of how it all fits together. But if we look down, we'll see that we come to a file structure section. So what this tells us is that the actual file that we will find on our SD card is split up into a number of areas. So the first 14 bytes of data, that is the bitmap file header, which tells us sort of general information about the way in which the file is organized. We'll then find that there's a second block of data, which is this DIB header, and that will store a number of information about the size of the image and how the pixels are actually formatted. We then come to a number of optional areas. Depending on how the image is stored, we might have some compression information, we might have some color information, we might then have a small gap in the data, and we'll see how we can detect whether there's a gap there or not when we come to parse the file header. There's then the actual pixel data itself, some other sort of alignment issues, and then some color profile information. So this all sounds sort of quite complicated at the moment, but if we then go down a bit further, we'll start to see how this is all broken down. So each of these sections then is just a series of bytes of data. And those bytes of data then obviously mean something, and we have to read them in a certain way. So if we look at the bitmap file header, so this column here tells us its offset within the file. So if we open a file using our SD card open file method, we will end up with our data pointer sitting at the very first byte of that data. So as we start to read bytes, we will start to read them in this order. So the first 2 bytes we read in is this header field value, which identifies what type of file this is. So it's a 2 characters or 2 bytes. And we're expecting those to be saying BM for a bitmap file. But there are other versions here. And again, as we write our code, we will probably decide that we will only filter out files which have this code BM in them. Otherwise, we'll have to obviously then write code to handle all of these other file formats. So they're all bitmap file formats, but they are all slightly different. So the next 4 bytes we read in, so this is a 32-bit integer number, that tells us the size of the whole file in bytes. We then have 2 16-bit numbers, so 2 bytes followed by 2 bytes, and those are reserved for further use. And we then have the next 4 bytes of data representing another 32-bit integer, which tells us the starting address of the actual pixel data. So remember, if we scroll back up here a bit, we have our bitmap file header, our DIB header, we have a number of optional bits, and then our pixel data. So this number, this 32-bit integer number, tells us the offset of the start of this block of data. So we can always get directly to the pixel information. So that's our bitmap file header, which is then followed by our bitmap information header, or this DIB header. And again, there's various versions of this. But what we'll find is there's actually a core that they all relate to. So that is the actual core, and there is then an example further down here of what's known as a bitmap info header, and this is the generic sort of header that we're going to find. So it includes the core plus a few extra values, and we'll find that all of the other variations in effect just include this and then extend with certain values after that. So we can really take this idea here as being our default. And again, if we look through that, we'll see then that, so the offset here, this follows on from the end of this bitmap header info. So 0A plus 4 bytes takes us then to 0E. Okay, so we're just simply reading in bytes after the header info, the bitmap header info. So the first 4 bytes is a 32-bit integer, which will tell us the size of this header. And again, that will usually be 40 bytes because that covers this header here. The extensions are less common. We then have another 32-bit integer, which tells us the width of the bitmap. Now this is usually a signed integer. Everything else is an unsigned integer, but this is a signed integer. And negative values do actually mean something, but they are not very common, so we're probably going to ignore that. So the next 4-bit value then, of course, is the height of the pixels. The next 2-byte number, so a 16-bit number here, is the number of color planes, and that has to be 1, otherwise we won't be able to read this value. Next, we're looking at the number of bits per pixel. So this is where we can have either 1 bit, which will give us a monochrome image, right up to our 32 bits per pixel, which is our 24-bit color plus 8 bits for our alpha channel or our transparency. So we're going to be dealing only with 24-bit bits per pixels. So we want to make sure that when we read our header, that we check this value for it being 24. Next, we have another 32-bit integer, so for another 4 bytes, which is the compression method, and we'll want this to be 0. We won't want to be handling any compression in our code. We then have another 32-bit integer value, so another 4 bytes for the image size. Then we have a further two 32-bit images which will look at the horizontal resolution, and this again is in effect our pixels per inch value. Again, it's pixels per meter here, but that's really what it relates out to, or dots per inch, whatever you want to call that. We then have the number of colours in our colour palette, and usually that will be 0, and that will just simply then say that if we've got a 24-bit bits per pixel, then we'll have 2 to the power of 24 colours in our palette. And again, then we have important colours used, and that really isn't a used value in it. But you can see here we have to read a number of bytes per value to get through this header. So really, that gives us the structure of our header information. After that, these, if I come back up here, these optional areas, we're really not going to bother with those. And as we've seen, there is an integer value in the bitmap file header which lets us jump straight across. So we read these two blocks of headers, and then that data value will let us jump straight down then to our pixel data, so we don't have to worry about reading this block here in these optional values, or actually worrying about them. So I've created an Excel spreadsheet that summarizes this data. So we can see here each of the individual data values, the size in bytes that we need to read in for each of those, and then what those values actually mean. So we can simply, when we open our file, we will simply start reading in these values, and then that will let us decode exactly how this image has been stored and where all of the pixel data is, so that we can go ahead and read that in and start sending that off to our LCD screen. And as usual, if you look in the description, you'll find a link to my main website where there'll be a page for this part of the project, and you'll find all of this data on that web page, along with any code, of course, that we develop during this video. So do make sure you do visit that and have a look for that information. To code this image format then, we'll make a start with our base code, which has our TFT or LCD screen information here, our touchscreen, and our SD card. And again, all this code, you'll find a link in the description down below. So it's just setting everything up and connecting it up and initializing those objects. So at this point down here, we should now have our LCD set up, our touch set up, and be able to communicate with our SD card. So I'm going to implement this bitmap file reader as an object, which will make it easy for us to then extract that at a later time into our own personal library file, which we could then use in other projects if we want. So if I just paste in my actual code there, and let's go through and see what this does. So if you're not familiar with using objects in C++, it is just a way of formatting data and functions. So we have to define something called a class, and this is in effect the template for our data structure for our object. So I'm defining a class, which I'm going to call a bitmap handler. Inside that class then, we have to define a number of data members or data attributes, and then functions, which we call methods when they're inside a class. So some of these are going to be what are known as private, and these are our data attributes and functions which you can only access when you're inside the object. And again, don't worry if this doesn't mean so much to you, but object-oriented coding is something which you really should get your head around. It does make things a lot easier when you come to develop more complex software. So really what I'm doing here is I'm creating some values within my object which are going to let me run that. So I'm going to have a Boolean file OK flag. So it's going to tell me whether the file I'm reading in is OK or not, and that's both in terms of whether we can actually access the file or whether it's the right format and so on. We're going to need some sort of file pointer which will let us access that on an SD card. So we're using a file object here, and that will handle that. And of course, we'll need to supply a file name for the actual file we're going to read. Now, as you saw in the explanation of the file format, we have a number of integers which are stored as individual bytes. So we'll have to have a way of reading in those individual bytes and then converting them into either our 8-bit, 16-bit or 32-bit integer values. So I've written 3 little methods in here which will do that for us. So really what's happening is we will ask one of these methods to read the next block of data, to translate that into an integer value, and then return that to us so we can then store that within our object. So there weren't any of the values which were 8-bit values, but I've put that in for completeness here. So really what we're saying is we're doing a check. So remember, we're going to be using this data attribute, so bitmap file is going to connect us to the actual file that we want to read. So if that hasn't been opened yet, then obviously we need to just exit out of here. Otherwise, we're simply going to read the next byte from the file and return that as an integer, because again, that will just be a single 8-bit value. It starts to get a little bit more complex then when we start to read our 16-bit and 32-bit numbers. So we know that our 16-bit number is going to consist of the next 2 bytes of information. So again, we're reading in these 2 bytes. Now, the data in a bitmap file is stored in what's known as little endian format. And what that means is that the 2 bytes of data, we will store the least significant byte first, and then followed by the most significant byte. So the first byte we read is the lower 8 bits, and the second byte we read is the upper 8 bits. So we're reading those 2 bytes in, and then we're just using this little line of code here. We're taking our most significant byte and we're shifting it up 8 bits to make it to the upper 8 bits of the 16 bits, and then just simply adding on the least significant byte. And that will then give us our full 16-bit number. Similarly, with our 32-bit numbers, we have to read in 4 bytes, and again, these are in little endian format as well. So we're reading in the lower 8 bits, then the second block of 8 bits, third, and then the most significant block of 8 bits. And again, we're then just shifting those along by doing this bit shift value. So we're taking our most significant byte, we're shifting it along 24 bits, and then just simply adding in the other ones behind it. And that will then build up our full 32-bit number. So that private set of data and all is going to be used by the class when it's processing the data. We then come into our public area, and this is both data attributes or variables in effect that we will be able to read from outside of the class. So in our main code, once we create an object and get it to read in the file and so on, we'll be able to then look at these values from the outside. Okay, so our public data here, and you can see all I'm doing is creating in effect a data attribute or a variable, as I said, to hold each of the values in those headers. So we've got our header field, and that's the one that will identify it as a bitmap, the BM image, the file size, and the image offset, which tells us where the pixels start. We've then got this DIB header that we went through with all the values in there, including the size of the image and the bits per pixel and so on. So what we will do when we create an instance of this object is that we will end up calling this function here. So this function has got the same name as the class, and that will make it into what's known as a constructor. So as soon as we create an object based on this class, this function here, or this method, will be automatically called. And we're going to pass in the file name then as a string object of the file that we want to process. So when we first instantiate our object then, okay, at this point we don't know if the file is okay. So we're going to set that file flag to being false, saying we don't yet have a valid file. we're then going to take this file name that's coming in as a parameter, and we're going to store that inside our objects data attribute, this BMP file name. I remember that was one of the private ones. So we have a log of which file we're working with. We're then going to try and open that file in read mode. And if that file doesn't open, we're going to serial print a little error message, and of course mark this file as not okay. And at that point, we will then actually exit out of our constructor function, because all of this block here will be skipped over, and we will then not be able to work with that. But if that file is okay, so at this point here we've been able to open the file, we're then going to go off and read the file headers. So let's have a look at what reading the file headers actually does. So this function here, so it's going to return back a Boolean value whether it managed to read the headers or not. And again, that will then let us work out whether this file is in the right format or not. So again, we're making sure that our file is open. And we're then going to reset any file pointers back to 0. Okay, so we may have been doing some reading of the file in other ways. So this just confirms, or just makes sure that our file pointer is pointing at the very first byte of our file. So we then start reading in the headers. So we're reading in each of these data values. So remember, these are all the data values defined in our headers, and we've then created individual data attributes to hold each of these. So our header field value is the first 16-bit integer that we read in, and then we're simply going through reading them all in here. So remember, we had two 16-bit integers which were reserved for various applications that create these bitmap files. So we still have to read them in, but we don't need to capture the value. So we're just reading in a 16-bit value and just throwing it away. So as we go through all of these reads, we will then be building up all of the header values as data attributes in our object. And when we get to the end here, we will then either return back true, we managed to read all those headers, or false, that there was something wrong and we weren't able to read those headers in. And in effect, at this point, it just means that the file wasn't open. So coming back up to our constructor function then. So we are calling this inside an if statement. So that actually will execute the function to read in the headers and then check its return value. So we said if this returns back a false, then we weren't able to read that in, and we take the appropriate action and mark this file as not okay. So if the file headers are read correctly, then we want to check them. So again, we're doing a very similar thing here where we're going to call a method called check file headers. So if we come down to that, and this is where we are reading in and examining those header values. So we said that our first header value then is the header field, and that needs to be equal to this character string BM, and in hexadecimal that's going to be 4D42. So if our header field value that we read in during our read file headers, so there's the first 2 bytes, if it isn't the BM, then we're going to return back false, which is going to signify that we have not got the correct file type. We're then checking our color plane value, which must be equal to 1. We're then checking our bits per pixel value, which must be 24 bits per pixel, because that's the only one we're going to be dealing with here. We don't want any compression, so if all of these checks pass, we will return back true, otherwise we'll send back false for each individual one. So back into our constructor function. So again, so if the check file headers returns back false, then that's an error and we mark that. Otherwise, we're going to say this file is all okay and we're going to mark it as okay. Yeah. So once we come out of this if statement, so this if statement matches up with the file being able to be opened. So once we've got through reading in the headers and checking them, we then want to make sure that we close our file so that when we exit out of our constructor function, our file is closed so that we can then carry on and work with that at the next operation. If I come down to the setup function, again, normal idea here where we're setting up all of the bits of hardware. So at this point, we should now be ready to do some coding. So if I paste in there our object declaration, so we're creating a variable called BMH for Bitmap Handler. The type of this variable is going to be the class Bitmap Handler. And the way in which we instantiate that variable then is we are calling the Bitmap Handler, and that will of course call that constructor function. And we need to pass in a string, which is going to be the file name that we want to use. So I have another file on there called balloons.bitmap, which is another 24-bit bitmap file. Again, I've sized all of these bitmap files to fill my screen, which is a 320 by 240 pixel image. So we should be able to upload that into our Arduino and get back some information about our bitmap. So let's just upload that into our Arduino. And I'm going to check on my serial monitor. And there we have our response back from our constructor saying that this bitmap file is okay. So at this point, our object does have all the information about that bitmap file loaded into its member attributes. So we could actually access those doing our BMH dot, we could get the header field value in that way there. And we could have a look at what those actually are. But what we could also do is we could create an extra little function or method inside our class which will actually print out all the details about this file. So let's create a new method in there called serial print headers, which is basically going to take all of that information it's just read in, all that header information, and print that out on our serial port. So if I scroll up to this function, so inside our object, I've already created this method called serial print headers, which doesn't return any values. And it's really going through each of the data attributes in our class and printing those out, so telling us what data field this is and then its value. So you can see there we're just going through all of the actual values that we've read from our bitmap file. So let's upload that into our Arduino and have a look at our serial monitor. And there we have our bitmap file information coming out. So again, this is just reading in all of the header information from that file. So our file name, our header field value, which is our BM, our file size. The image offset tells us which byte is the start of the pixel data, our image width and height, and again remember I've saved everything on my images to fill my TFT screen. Our color planes are 24 bits per pixel and no compression. So that's all the information then that we need to make sure that this image is one that we can then handle with the code that we're going to write to now decode the pixel information. To work out how these pixels are stored, we first of all need to return to the Wikipedia entry on the bitmap file format. And we'll come to a section a bit further down which talks about pixel storage. So really what's happening here is that the bytes in the file represent each of the pixels in our image, and those are packed into rows. So as we start reading a series of bytes from the pixeled area, we're going to be getting individual pixels that will build the image up in rows. Now the rows that we're building up, if we look at this a bit further down, so usually those are stored as a bottom-up image. So the first pixels that we read in the file will represent the bottom left-hand corner of the image. And obviously on our LCD screen, usually we will use the top top left corner as the 0, 0 pixel. So we do have to make sure that the rows we draw represent the rows on the image. There is one other thing in here as well. We did see that whenever we looked at the height value in the headers, that was a signed integer. And there is, if we look at this bit here, there is a format they use. So if you find that the height value in the DIB header is a negative value, what that means is that the magnitude of that value is the actual height, but the fact that it's negative means that it has been flipped. So instead of going from bottom to top, the rows will be in the order of top to bottom. So that is something to look out for. I'm not going to handle that in this bit of code, but again, something you can obviously add in yourself at a later date. The last thing with the pixels then is that they have to be in multiples of 4. So whenever we create a row of pixels on the SD card bitmap file, we will take the pixels in a row. We're using 3 bytes per pixel, so our red, green and blue. And as well on that aspect, make sure that we understand that the color values will be stored in the order blue, green, red. So the first byte we read will represent the blue component, then the green, then the red. But when we create a row, we'll be using 3 bytes per pixel. But when we get to the end of the row, the total number of bytes used to represent that row must be a multiple of 4. So in other words, it's saying here the pixel array is a block of 32-bit D words. So we must end up at a 4-byte boundary. And really what we're going to do there is just simply, if we end up with, say we end up with 30 bytes worth of pixel information, then we need to make that up to 32 bytes. So we'll just simply put 2 bytes with 0 in them at the end of that, just to pad it out. So that's quite a complex way of looking at storing this data. So let me just summarize that a bit more easily by showing you a diagram with an image example. Let's consider a small image with 2 rows of 3 pixels each, and each of these pixels being a different color. So the way this would be stored on our SD card then is we will first of all take the bottom row and convert that into 3 3-byte sequences. So again, each 3-byte group will represent 1 pixel, and those will be stored in the order of blue, green, red. And similarly, our second row, so the upper row, will also be stored in the same way. So byte 0, the very first byte in our pixel data, will represent the blue component of the very bottom left corner pixel. For this row then, we'll have a further 8 bytes, making a total of 9 bytes, which will represent all the color values for those 3 pixels. Now our second row, because we need to be on these 4-byte boundaries, that must start at a byte which is a multiple of 4. And what this means is that our first row requires 3 extra bytes of information to pad that out, so that we have 12 bytes on our top row, which means that the second row will then start at this 4-byte boundary. And of course, since every row contains the same number of pixels, they will all require this same 3-byte padding. So let's come back into the code for our class, and let's add a render image method. So I have it already put into my class here. So we have our render image method, and for that we'll need to supply it with a number of parameters. These two, the screen X and screen Y, that will tell us where on the screen we want to place this image, and of course that's going to denote the top left hand corner. And again, for our screen coordinates, the 0, 0 position is actually in the very top left corner of the screen, and then of course we're measuring down from there. And as we've just seen, that's different to the way that the image is stored on our file. So we'll have to cope with that for a second. I'm also then passing in this reference to the screen object. So we know that if I go up to the very top of the screen here, we know that we have defined a global variable, this TFT, which is an instance of the ILI9341 driver that actually does the talking to the LCD screen itself. And we could, if we want, within our class, just reference that global variable, but that's actually not a good thing to do. Our class here, we may eventually want to extract that out and make it into a little standalone library, which we can then use and just simply import that into other Arduino projects. Now, if this library is relying on there being a named global variable, TFT, then obviously our other software has to have that global variable as well. So our library is now dependent upon a certain number of variables being in existence in our sketch, and that is not a good way to code. So what we're doing here is we are passing in a reference to that object. So whatever screen object we happen to be using in our sketch, we can just simply pass that in, and this class will now render this image on that particular screen. So that's just a bit of good programming practice for you there. Now, the actual render image function itself, if we think about it, this class will already have been instantiated using its constructor function. So when we instantiate this bitmap handler function, our constructor function down here will be called, so it will already know which particular file it's dealing with, and it will have checked that file, and we should now know that that file is able to be used. So when we come down to our render image function, we're going to have a block of local variables that we're going to be using as we parse this file. And I'll say we'll go through those as we meet them in the actual code itself. But at this point, we don't need to check the file. We just simply need to work out if the previous checks on the file all went okay. So at this point, if this data attribute file OK, if that contains a true value, then we know that our object has already read in the file information and checked it. So if it's not true, then we really want to just get back out of this render function without doing anything. We then want to make sure that the place where we've been asked to place the image is actually on our screen. So if it's actually off the edge of the screen, then there's no point trying to draw it. And that's all we're doing here, just doing some limit checking. And again, our screen.width, that's a method in that ILI9341 driver software that actually tells us how wide the screen is and how high the screen is. So the image that we're going to use, we have already then, as I said, read the header information, and these two data attributes, image width and image height, we will have set that elsewhere in this class, and that will be the actual image file pixel width and pixel height. So we need to make sure how much of this we actually need to draw to fit it on the screen. So we start off by just saying our displayed width and our displayed height. So this is the number of pixels we're going to draw on the screen. We set those to the full image width and image height. We then check that if we place the top left corner of this image at these positions, screen X and screen Y, is it going to fit on the screen? So if it does fit on the screen, then that's fine. We just leave those displayed width and displayed height as they are. But if it's actually going to go off the edge of the screen, we then reduce our displayed width and our displayed height values to only show the number of pixels required to hit either the right-hand edge of the screen or the bottom of the screen. So we're really just going to clip it at that area. And that's all that block of code there is doing. So at this point in our code, so once we reach this line down here, we now know that our image is correct, or at least it's a file that we can work with. We know that if we place it at screen X and screen Y, we know that if we write out this displayed width and displayed height rectangular area, then that image will fit on the screen. So we've got everything ready to start actually putting pixels onto that LCD. We now need to work out how we can grab hold of the pixel information out of the bitmap file. So we've already seen that each row of pixels is stored in the bitmap file one after the other. Now we want to be able to pick out a particular row so that we can then draw that on our LCD. So we'll need to be able to access each row, and the way we do that is to look at our pixel data offsets. Remember, we had up here somewhere, we had our image offset value, and that was the byte address within our SD card file of the first byte of pixel image data. So position image offset in our file gives us the first byte of pixel data. So coming back down to our render function. Okay, so to get a particular row, we need to move to that pixel data start position. If we want to get the very first row, then we just start reading data from there. If we want to get a row that's higher than that, we then have to skip a number of blocks past that start position. Okay, and the size of each block will be the size of one row of pixels. So we need to work out how many bytes are needed to store one row of pixels in our image file. And that's what we're working out here. So we know that we're using 3 bytes per pixel. So 3 times the image width will give us the total number of color bytes of information in this row. We then know that each row must contain a multiple of 4 bytes, and that's what we're doing here in this block. So that is the number of bytes of color information. The percentage sign here is the modulo operator. So modulo 4 will in effect do a division by 4 and tell us what the remainder is. So that will tell us how far into the last block of 4 bytes this color information goes. So if in our previous example we saw that we had 9 bytes of color data, so 9 modulo 4 would be 1. So 9 divided by 4 is 2, remainder 1. So this would give us 1. That says we are 1 byte into the next block of 4. So if we do 4 minus this value, that will tell us how many bytes we need to add on to get us to the next 4 byte boundary. So again, in our example, so 9 modulo 4 gives us 1, 4 minus 1 gives us 3, so we need to add on 3 bytes to give us that full 12 byte row. Now the problem we have is that if we happen to be actually on a 4 byte boundary, then our color byte width modulo 4 will actually give us 0, which will mean we're saying we need 4 bytes to get to the next 4 byte boundary. Which is in a way true, but we're actually at a 4 byte boundary. So if we modulo that number by 4 again, that will make sure that if we do get an answer of we need 4 bytes to get to the next boundary, this will bring it back down to 0, because again 4 divided by 4 is 1, remainder 0, so the modulo gives us 0 there. So adding total number of color bytes to the padding bytes, that gives us the total number of bytes for each row of pixel data. So once we've calculated that, we've really got all the information we need to start writing as pixels. So the next line then is, of course, to reopen that file. And then we're going to use one of the low-level functions of our LCD graphics library. So again, the Adafruit library has got a number of functions to draw things like lines and so on, but it also has some lower-level functions where we can simply write pixel information very quickly out to the screen. And what we're doing here is we're using this set address window. And what that lets us do is to define an area on the screen. So a rectangular area, and you can see here we're using our screen X, screen Y to be the top left corner of this area, and then that area is going to be display width pixels wide and displayed height pixels tall. What then happens is all we have to do is start sending pixel color data out, and our LCD screen will simply take the area that we've now set as the active area and start filling it from this top left corner position. So it will fill the top row of pixels first, and we just simply keep sending it pixel information until it fills up that whole target area. And that is a very fast way of writing out to these LCD screens. Remember, everything goes across this SPI channel, which is a serial channel. So in effect, it is a slow way of doing it. But this means we don't have to send lots of other command information around it. We just simply say, here is an area I want you to fill, and then we just blast out the color pixel data. Now you'll see as well that we've had to surround that method call with a start right and an end right. So when we need to talk to the LCD screen, we do need to make sure that we address that. So we have other devices sitting on our SPI channel. Again, we have our touchscreen and our SD card itself. So what this does, the start right initiates the conversation and tells the SPI channel to talk to the LCD screen. We then send the LCD screen some command codes to set up the address window, and then we tell the LCD screen we have finished talking to you. And it's important you do that, because obviously if we leave the channel open to the LCD screen and then go off and try and access the SD card, our hardware is going to get confused as to which SPI device we're actually talking to. The higher level functions in the graphics library handle all this for you, but now we're working at a very lower level. We need to start initiating these conversations and closing these conversations ourselves. So at this point we open the channel, send the commands, and then close the channel so we can now talk to other devices. A little bit of debugging here, so just so we can see what's going on inside our system, and then we get into the actual pixel data. So we're going to use two for loops. So our first for loop will handle the rows, and then our inner for loop will handle the actual pixels, or in fact the columns. So our first row for loop, that's going to loop from row 0, which is the top row as displayed on our LCD screen, and it will count down displayed height pixels from there. So that's all this loop is doing. Now, to get hold of the pixel information, we need to be able to pull out a particular row's worth of data. And we know that if we're drawing the top row in our LCD display, that's actually going to be the last row stored in our SD card file, in the bitmap file. So we need to be able to work out, for any particular row that we're drawing, where in the bitmap file is that block of data stored. So we need to calculate an offset value. So that is the byte position within our file where the start of this row's color information is. And that's what this calculation is doing here. So this image offset, that's a value we've read from the header of the bitmap file. And that tells us the very first piece of pixel data. And of course, that's the very start of the very bottom row of pixels on the image. This bit of code here, that tells us how many rows above the bottom row the pixel row that we're looking at is. So pixel row is the LCD screen row that we want, and this tells us how many rows that is above the bottom row in the actual image. Then for each row we need to skip ahead bytes per row bytes. So this calculation here, so that's how many rows above the last row we are, times the number of bytes per row, added on to the offset of the very first row. That should then give us the starting byte position of the first byte of information for this row's pixels. Okay, so that's all we're working out there. Because what we're going to make use of is the idea that in these files, as we read them from our SD card, we're working with what's known as a file pointer. So far we've just simply opened a file and we've started reading, and we've got the first byte followed by the second byte and so on. But what the system is actually doing is it's keeping a track of which byte we're about to read. So when we first open the file, it sets this file pointer to 0. So the first byte we're going to read is the very first byte in the file itself, so position 0. As we then read a byte, that file pointer moves on to position 1. So the next time we read a byte, we'll read byte position 1, and so on. But there is a special method within our SD card handler that lets us reset this file pointer to wherever we want. So we don't have to read things sequentially. What we can do is we can actually say, okay, I've calculated an offset that I need to get to, so I can simply set my file pointer to that offset, and then as I start to read bytes of information in, I will read them starting at that position. And that's what we're doing here with this seek method. So we do need to make sure that our LCD, so this is just making sure that we are not talking to the LCD screen. So we're saying to the screen, end any writing that you're doing at the moment. We then have, obviously, this BMP file is one of the attributes in our class, and of course that is a connection, a file connection out to the file that we're reading from the SD card. So we're setting the seek method and we're setting its file pointer then to the first byte of the row of data we want. We're going to be writing individual pixels out to this LCD screen. So to speed that up a bit, instead of reading a pixel from the SD card, then writing it out to the LCD, and then going back and reading another pixel from the SD card, and so on, we're going to try and do it in blocks. So we're going to read a block of pixels from the SD card, and then we're going to write those out to our LCD screen. So I've created a little pixel buffer here, and a pixel buffer counter. So really what we're doing is, if I just scroll up just a wee bit, we have created a pixel buffer. So that's using these unsigned 8-bit integers. Okay, so a single byte of information. So that's an array. I'm doing 10 pixels at a time, and of course that means that I will need 30 bytes to store 10 pixels worth of color data. I'm then using a pixel buffer counter, which in effect is like a file pointer, which is going to tell us where in the buffer we're currently reading from. So initially we're going to set that to the end of the buffer, and that signifies that the buffer is empty. So in other words, we've got to the very last pixel in our buffer, which means that, of course, then that it needs to be refilled. So if we come back down to our column for loop. Okay. So again, we initialize our pixel buffer counter to the end of the buffer, so that signifies that it is empty. And what we're saying is, if our pixel buffer counter is at the end of the buffer, in other words, we've used up all of our pixels, then we're going to read in another block of pixels. So again, we want to make sure that our screen is not being talked to. We then use this read function. Now the read function, so far we've just been doing read with a pair of brackets after it. There is an extended or an overridden version of that read method where we can give it an array and then a number of pixels that we want to read into that array. So again, our pixel buffer has got 30 elements in it. So we simply say read from our file into our pixel buffer array and then size of pixel buffer bytes. So again, that will be 30. So this will read in a block of 30 bytes of information into our pixel buffer array. At that point, we set our pixel buffer counter, which again is our pointer, down to 0. In other words, we are now reading from the first position in our array, which of course is index number 0. And then we turn back on the ability to write out to our LCD screen, because most of this loop is going to be writing to the LCD screen, just with a very short pause in that writing process where we read in some more pixels. So as this loop goes through, we initially fill up our buffer. Then we know that the data that we read from our SD card is in the order of a blue, green and red pixel bytes. So the first byte we read then from our pixel buffer is going to be the blue information. We read it from the pointer position, and by putting ++ after pixel buffer counter, it will perform this read first. So we read this particular byte of information, and then it automatically, once we've done that, increments pixel buffer counter, so it points to the next byte. We then read in the green pixel, and of course that has now been pointed to the next byte. After we've read that, we then move on one more to the next byte, and then we read in our red byte. And after that again, we move our pointer on one, so the next time we come round, we will be ready to read in the blue one again. So we read in 1 pixel's worth of data, and then we write that out to our screen. So we have the special screen.writeColor method. We need to supply it with a 16-bit color value, because that's what this LCD screen works with. So there is a special method within the screen driver, which is this color 565. We then give it an R, G and B values, and we tell it to output 1 pixel. So that's what's happening here. So that creates the 16-bit color value from our 24-bit color value, and we say write that out to the next pixel. And then our loop goes through. So at this point, our pixel buffer counter is still somewhere inside our pixel. It hasn't got to the end of our pixel buffer. So we simply then send a byte, a byte, a byte, and then after 10 bytes, we come back round and our pixel buffer counter has now reached the end of our buffer, and we then read in the next block of data. Okay, so that lets us then work through each row, finding the start position of that row's color bytes. We then work all the way through that row, outputting each individual pixel, and then we come back up and we start the next row. Okay, so in this way we are working our way from the top of the LCD area to the bottom of the LCD area, while simultaneously then working from the first or the last row of data in our file image towards the first row of image data. Right, so that should give us our pixels coming out. Of course, once we've finished the last row, we need to make sure that we end the writing process to our LCD screen. And at that point, we've finished with our file, so we need to close our file. Remember, it's always a good idea to close your files when you finish working with them. So that really should let us now write our image to the screen. So if we come back down to our main function, okay, so we have instantiated a bitmap handler object. We are outputting these headers so we can see what's going on. Then the last thing we do, of course, then is call this render image method. So our bitmap handler, the bmh.renderImage, pass it in a reference to our global variable, which is our TFT handler object, and then tell it to print it in the very top left corner, so position 0, 0. So let's give that a go and see if it works. And there we have our bitmap displaying on our screen. So we can start to have a bit of a play around with this then. So we know that if we position our image slightly away from the edge, so that's 50 pixels across and 100 pixels down. So we've now got that larger image positioned on the screen but being clipped at the right hand and bottom edges. And then I've also got a smaller image in here. So remember, these images at the moment are full size on the screen. But I have an image called small. And there we have that image now displaying completely on the screen with, of course, borders then to the right and to the bottom. So we've really now got a little library that lets us specify a 24-bit bitmap file, position it anywhere on the screen, and it will then be drawn either full size if there's enough room or clipped to fit onto our LCD screen. So we can then use this now for positioning images around, maybe as an actual photographic background for our control panels, and on top of that we can then draw the needles for each of the dials and so on, or just some sort of decoration on our screen, or some splash screens, or whatever we want to do with that. So as a last little play around, I've written a little slideshow application. So it's using pretty much the same software. I've added a few extra bits in here where it's going to handle reading the images or the image file names from our SD card. All of this code and the sketches themselves, you can download them from my website, and I'll put links in the description down below to the page for this project. So do visit that to get hold of all of this code. The bitmap handler class is exactly as we've developed in the rest of this video. I did make one little change. I did say there's one error that I had missed in the render image method. I had only been checking for the screen coordinates. Remember, we give it the top left corner of where we want the image to be. I checked for it going off the right hand edge and off the bottom, but not going off the left hand edge or above the top. So I've just added that in there, just checking that they're not less than 0 at either of these values. But the rest of it then, if we come in our setup function, so after we've initialized all the hardware, all I'm doing here is I'm opening up the root folder of the SD card, and I'm using some of the next file functions. So what we can do here is we can just open up the SD card at the root directory. So that's setting my directory pointer to the root directory. I'm then creating a file object which is going to hold the next file name. So I'm really going through, I'm initializing my images array. So I'm creating an array which is going to hold the file name of each of the images that I find. And then I'm using a while loop here. So while there is a next file to open, I check if it's a directory. So if it's not a directory, then we check to see if it contains .bmp in the file name, and at that point it will log that in my images array as a file that we need to process, and it just simply loops round through that. So every time we call the method open next file, that checks to see if I have another file to work with, and again that will then create an array of all those file names. So after that we just simply close those files down. And then in the loop, the main loop of our sketch, all we're doing is we're keeping a little counter as to which image we are currently showing, and we're just looping through our array, initializing our bitmap handler to work with that image, showing it on the screen, and then waiting for 1 second before we go off and find the next image to show. So let me just show you that working. And as our sketch runs then, we get our first image, and then we have our slideshow working through each of the images that I've saved on this SD card. And we can see there with the small image then, it obviously only overwrites the area of screen that actually contains the image. So that's where you can start to use background images and then put other images over the top. Or as I say, if you were doing something like a control panel, you could then draw various needles. So you have a nice display for your control panel, and then just filling in the needles and only needing to draw those each frame to show your results. So that's another project then using our Arduino, our LCD screen and our SD card. And we've seen then how we can just simply, any file that is on our SD card is just simply a collection of bytes of information, and we can then write some software to look at those bytes of information, decode them, and then in this particular instance then using a bitmap image, translate that data into actual pixels on our LCD screen. But hopefully that's shown you that this idea of using our SD card, we access it using the Arduino at a very low level and just treat any file at all is just simply a block of data. And providing that we know the format of that data, again we've looked this up on Wikipedia, we'll be able to interpret that and then handle it in whatever way we want. And of course, going the opposite way, creating files, as long as we know that data format, we can of course then write those bytes out onto our SD card in the correct format, and then that will be readable in other machines. So hopefully you've enjoyed the video. If you have, please do consider hitting that subscribe button down below and turning on your notifications so that you are notified as soon as I create any more content. So hopefully I will see you in another video very soon, and bye for now. Don't forget to visit the course pages for this project. There you'll be able to download the code for this lesson and get lots of extra hints and tips. You'll also get access to all my other programming, electronics and gaming projects. All the links are in the description below. For more games programming, electronics projects and retro gaming, please make sure you like this video, subscribe to my YouTube channel and visit my website.